Our presenter for today is Theo Chawla. Theo Chawla. Theo is a second-year master's student at Wesleyan, and appreciate him coming in. This talk is going to be on circumstellar disks and planet evolution, and I'm going to let Theo do the details on that. So I'm going to stop sharing my screen, and we're going to switch over to the presentation from Theo. So hang on. As I fumble here. Stop share. There we go. Okay. Let's see. Escape. Okay. File open. Give me a minute here. Hartford AS Talk, right?
Yep.
Okay. Yeah, just want to be able, I just want to get their sharing. Hang on a minute. Ugh. Come on. I'm trying to switch over to the Zoom workplace so I can share it. There we go. Mhm. No, I'm not sharing. That's why I'm trying to get over to the Zoom workplace so I can share Theo's screen. Windows. I've been doing that, John. Oy. All right, give me a minute here. The heck? Oh, okay. Jeez. Okay, good.
There we go. We got you.
Okay, I'm just gonna leave it alone now. All right. You gotta get closer. I don't think, yeah.
My guest tonight is Theo Chawla from Wesleyan. I would like to ask everyone, please. Talk. I want to express my continuing gratitude for Wesleyan Association. I gave Professor Hughes a call, email early in our season, and Theo's is one of the first one to say yes. So Theo's interest is in circumstellar disks, exoplanets, and planetary formation, and it sounds like he has an interesting.
Chris, you're fading in and out as for us online. We cannot. I mean, we get about 4 or 5 words and then you fade right out.
Okay. I'm almost done anyway.
Okay.
Anything you need me to repeat? So again, I'll introduce Theo Chawla. Go ahead.
Okay, great. And hopefully everyone can hear me okay. Like Dean mentioned, I'm a second-year master's student in the Wesleyan Master's Astronomy program, and I'm so excited to talk to you all today. This is my favorite thing in the world, is getting to talk to people about my research. Usually people are trying to make me shut up about research. So I just wanted to give you a little bit of background about myself. Like Dean mentioned, I kind of had an unconventional path to astronomy. So I started by studying graphic design and got involved in astronomy research while I was doing that. And I just totally fell in love with it. So I went to community college and I got a couple jobs working at observatories and local science centers. And I really loved doing outreach work. This is me up here operating the 36-inch refractor at the observatory, which is just the best job in the world. Research-wise, I've mostly focused on exoplanet stuff, so I've worked on exoplanet transits, some instrumentation on building new technology on how to observe exoplanet atmospheres from the ground. But for my thesis project, I'm mostly focusing on circumstellar disks, and that's what I want to talk to you about today. So just to give you a quick overview of what I'm going to cover and just an outline of my talk. So I'm going to first talk about debris and circumstellar disks and how we see them and why we think they're interesting. My thesis project is focused on this very specific debris disk called Ceti. So I'll talk a little bit about the object and why it's so bizarre. And then really focused on warps and spirals in disks. And so I'll give an overview of how they appear in other disks and some of our initial results from analyzing Ceti. So just a brief overview of debris and protoplanetary disks, why they're interesting. As a star forms, you have this big cloud of gas that starts collapsing into a nucleus. In addition to this dense ball of plasma that forms as the star, you also get this really thick gaseous cloud of dust and gas that forms around it, called protoplanetary disk. And as the name kind of hints at, we think these disks are really interesting because we think tiny baby planets are starting to create and form within the disk. And for a really long time, I didn't actually think that we could observe planetary disks, any kind of circumstellar disks at all. I was under the impression that they were too ephemeral, too faint, and we just didn't have a good way to view them. But yeah.
Sorry, I'm gonna
Sure.
Getting complaints that the volume's cutting out.
Okay.
I'm gonna disconnect these microphones and we're gonna go with the microphone that's
Sure.
on the camera. That seems to work better for the most part.
Sure, no problem.
So. Sorry. Can you guys hear me online?
You have one in your shirt too, is that up?
It's hard to hear them here.
Well.
Oh, is it hard? Okay, I'll speak louder. Thanks for letting me
That's
know.
why I moved up.
The receiver's not connected anymore, so these don't matter anymore.
Okay,
Can you guys hear me online?
should we move the podium forward a couple feet and I can move back? For Al.
Is the anybody responding there?
Us.
Yes,
Yeah.
Chris, that sounds better.
Okay. Okay, let me just move this closer. We've had problems with these before.
AV is always the hardest part.
Yeah.
Like this.
If you could maybe try to speak up a little.
Sure.
I know your voice is kind of quiet.
Yeah, no, thanks for letting me know.
All right.
Yeah, so I'll just try to speak a little bit louder. Hopefully this is a bit better. Yeah, okay. So it turns out that we can actually view these disks. And to do that, we use this incredible radio telescope in the Atacama Desert called ALMA. That's the Atacama Large Millimeter Submillimeter Array. It's a collection of 66 radio antennae that are about 12 meters in diameter. And they can be individually driven around this huge plain in the desert. The greatest distance that you can get between two radio dishes is about 16 kilometers. And when we combine the data from all of these dishes, we're able to get really high resolution, really high spatial resolution images of even faint objects that emit at radio wavelengths. And so that's how we're looking at these protoplanetary disks and debris disks also. And so just to give you an idea of the kinds of images that we can receive, we're just starting to get into the phase where we can look at the fine detail within protoplanetary disks. So this was a large survey that was conducted in 2018 called D-SHARP's the Disk Substructure at High Angular Resolution Project. And what I think is really incredible about these images is that you can start to see rings and gaps and spirals within the disks where planets are beginning to carve out spaces within them. So we're coming into this era where we're starting to see planets really impact the structure and kinematics of these disks. We're looking at the dust in the disks here, but we can also look at gas emission and get a sense of the gas in the disk. So this is another large survey looking at the carbon monoxide emission. And I love these images because you can really get a sense of the shape and the structure of the disks. Like they really look at the protoplanetary phase, like these big fluffy donuts that are optically thick, that are opaque to us. So just really, really beautiful images and a huge variety of systems. These disks evolve over time. So they start as these big, fluffy, opaque donuts, really gas rich. And over time, they slowly dissipate their gas and the dust gets blown out of their system. And what I study in my research are these later evolutions, these debris disks that are thinner, they're more dust rich than gas rich, and they're a little bit less luminous, a little bit older as well. And the dust that we see in these systems is actually not inherited from the protoplanetary phase, but it's created in a process called the collisional cascade, where we have these chunks of rock that are collide with each other and grind down to smaller and smaller pieces. And that's really the dust that we're seeing in these debris disks. My fun fact about our solar system is that we also host a debris disk. So our asteroid belt, the dust between our planets in the inner solar system, and then our Kuiper Belt on the outside are all considered part of our debris disk. And we can actually see the shape of the disk in something that we call the zodiacal light. I've never gotten to see it. I've never been in a dark sky location that could really highlight it, but you can see it right after the sun goes down if the sky is really, really dark. So you can see it kind of in this arc that's coming up from the horizon, this line that's not coincided with the Milky Way, but is on the line of the ecliptic. So on the same line as we would see the moon and the planets and the sun. And I just think it's really, really beautiful. And very recently, actually, these results were just published at the beginning of this year. We've started to do these large surveys for debris disks as well. And we're beginning to understand the substructure and where the dust is in these disks from the debris disk phase. And I've given you kind of a precursor. The disk that we're going to be focusing on is 49 Ceti, which is just in the upper left-hand corner there. And that's what I've spent the last year. All I've been doing is looking at that disk. So, and so I'm going to talk about why I think these disks are really interesting. We have protoplanetary disks that we see just as these planets are starting to form, and we can observe exoplanets after they've formed. But I think debris disks are kind of right in the middle. You can start to view planets and these systems that host them in the process of formation, and just as they're starting to accrete and come well together. They're also not super well studied yet because we're just developing the tools now to be able to view them. And we're starting to get a good idea about how planets might be impacting the structure of these disks. As opposed to protoplanetary disks, which are very opaque, debris disks can be relatively transparent. And so if we're looking to take images directly of exoplanets, debris disks might be a really good place to look for them. So a couple of reasons why I think they're really cool. And I want to dive into this particular debris disk and why we're scientifically interested in it. So just to introduce you, this star 49 Ceti is about 57 parsecs away. So on the scale of like 150 light years or so. The star is about 40 million years old. And by this age, we would have expected that protoplanetary disks, and as they evolved into debris disks, we would have expected that they totally dissipate their gas. But 49 Ceti is actually gas bearing, so it has this population of carbon monoxide that we can see at radio wavelengths. We think this is really unusual, and we don't really know where the gas is coming from. So it's this really interesting open question. The star is also a little bit more massive than ours, about 2 times the mass of the sun, and the disk itself is a little bit larger. It's right now we don't have the technology to image debris disks that are the size of our solar system, and so the ones that we can see are typically a little bit bigger. So this is a composite image of 49 Ceti. It looks like a blurry blob, but in the red, you can see the distribution of the dust. In the blue, you can see the distribution of carbon in the disk. And then in these overlapping areas where it's kind of orangish, that's where the carbon monoxide is. We also have very recently also, just last year, some really interesting data was published as viewed by the James Webb Space Telescope. So we see this disk at radio wavelengths, but we also see it at shorter infrared wavelengths. And we see this carbon monoxide fluorescing at these mid-infrared wavelengths. And in fact, you can see in the spectrum on the right side, it peaks at several different wavelengths. So we can see these different transitions in the carbon monoxide. But I really want to focus on the radio data. I kind of live in radio land, and so I want to focus on the carbon monoxide observations. And so in this plot, we have the carbon monoxide emission in the color in the background, and on the left, we have a model of the disk as if it was perfectly symmetric and everything was rotating in a completely Keplerian manner. And something really interesting happens when we subtract that model. And it reveals these asymmetries in the disk that were really subtle and you wouldn't have revealed otherwise. So when we subtract this model of a completely symmetric disk, we see these 2 branches of emission on the top and the bottom that are kind of maybe a little hand wavy, but maybe looks like a little bit like spiral arms within the disk. And so that is really what we're interested in investigating more. And if we image those residuals, that leftover data directly, that leftover data after you subtract that symmetric model, here's just a clearer image of it. So we see these 2 branches of emission that are offset from the major axis of the disk. And then we also see some positive and negative features. So we see some chunks of the disk and, kind of that bluish, yellowish white color that are moving faster than we expect. And that chunk of blue kind of right underneath of the disk where that portion is moving a little bit slower than we anticipated. And so we're trying to figure out what this is and why it's happening. But a really interesting thing about the disk is that we don't only see this feature in the gas, we also see it in the dust. And so we can see the dust continuum over here on the left. That dotted line is the major axis of the disk. And those peaks of emission are actually offset from that major axis. And it's a little tough to see in this figure on the right here, but if you map in green where the carbon monoxide offset is as compared to the continuum, they're kind of going in the same direction. They're not exactly in the same place, but it's this indication that this feature is occurring in both the gas and the dust, and it probably has the same origins. So I want to talk a little bit about warps and spirals as we see them in other disks, because that's kind of our initial hypothesis. Maybe what we're seeing in this disk is a kind of global spiral or a warp where part of the disk is at a different tilt than the rest of it. And so we want to look at how those appear in other disks and see if that's a probable explanation. So just to give a visual demonstration, we have a warp over here on the left where maybe the outer part of your disk is at a different tilt than the inner part of your disk. And then we have a spiral on the right where you have a spiral-like structure, but everything is within the plane of the disk. And of course, we see spirals in other places in the universe. The most prominent example, I think, is definitely in our spiral galaxies. We think that these spirals are caused by gravitational instabilities, which occur when you have a lot of gas in your system, a lot of massive gas in your system, and it's relatively cool. And these spiral arms propagate as density waves. So they're portions of the gas that are a little bit more dense than the portion right next to it. And something really interesting about spirals that I didn't know until taking classes at Wesleyan was that the rotation speed of the spiral is actually different than the rotation speed of the galaxy. So if you have an individual star, it might pass through a spiral arm, but the spiral arm might be rotating slower than the rotation of the material in the galaxy. And we kind of expect this to be the same for other types of disks as well. So in terms of gravitational instabilities, we see them in galaxies, we see them in protoplanetary disks. We know that a requirement for them is that the amount of gas that you have to have in your system has to be relatively high. And there's also parameters for density and temperature. So you want your density and temperature to be a little bit lower. So examples of this that we see in protoplanetary disks. So that's this earlier phase and disks around stars as this infall is happening. I don't know if you can see it for Elias 227, but it has these two beautiful spiral arms that are kind of arcing out from the disk. And a couple other examples are MWC 758 and AB Arye. And
Simulations.
these, actually, this one on the right is simulation, but these two on the left are actual images. So these are taken. That's a really great question.
I mean, our left and your.
Oh, sorry. Yes. So the two on the left, yeah, your left, and now my left also. Those are real data, and then the one on the right is a simulation. Thanks.
Where do you get those images?
These images are from the ALMA telescope. I've pulled them from literature papers that have been published about protoplanetary disks. But if you wanted to find them, well, if you're interested, I can send you the papers. I don't know if that would be interesting to you. But...
Weren't taken at Wesleyan University.
Oh, I wish. That would be
Radio.
really incredible. But no, they're taken with that big radio array that I showed at the beginning. Yeah, I think so far, other than, at radio wavelengths, I think that is really the only instrument that we can see these disks at really high resolution. And I'll also mention, if you have questions, feel free to interrupt me, because that's definitely the most fun part of this. So. But gravitational instabilities aren't the only types of spirals that we can see. We can also have companion-driven spirals. So a planet or a moon or an extra star might drive spiral systems. So we see this in planetary rings. They haven't been observed in debris disks, but we can model what they would look like in debris disks. And I think one of the interesting things is they don't depend on this gas mass. It's instead a gravitational perturbation that's caused by the companion. And I think a really gorgeous example of this are the spirals propagated in Saturn's rings. These are images from Cassini, and I'll take any excuse to look at a great Cassini image. But over here on your right, you'll see these spiral waves that are being propagated through the disk. Each crest of these waves occur when two moons of Saturn, Janus and Epimetheus, switch positions on the same orbital track. This happens about every 4 years. And so you can see this dynamic history that's being propagated through the disk. I think a more direct example is Daphnis, which we see on the left. The disks interior to it are moving a little bit slower, and the disks interior to it are moving a little bit faster, and the disks exterior to it are moving a little bit slower. So the gravitational effect of Daphnis is to pull those inner disks backwards a little bit and push the outer disks a little bit forward. So we see this spiral pattern that gets propagated through the disk. And I want to talk just very briefly. I won't go into too much detail on this, but just so you have a little bit of context on how we view kinematics in disks. When we view gas in disks, we see the gas emit at this very particular wavelength or frequency, which we call an emission line. And can you raise your hand if you've heard of the Doppler effect? Yeah, so maybe we're pretty familiar with the Doppler effect. So as the disk rotates, the portion of the disk that's coming towards us is blue shifted, and the portion of the disk that's moving away from us is red shifted. So it kind of spreads out this range of frequencies across the emission line. And what's something that's really incredible about ALMA, the radio telescope that we use, is that we have a spatial image for each portion of this frequency spectrum. And so if we can single out the portion of the disk that's a little bit more redshifted than another, we can see how the velocity changes in the disk and get an idea of how it's rotating. And so I wanted to show you that before I show you some of the kinematic effects that these spirals can have. So I mentioned here the images at the bottom. Those are images of the disk at particular frequencies or velocities. We call these channel maps. the effects on these channel maps that spirals have, whether they're planet-driven or gravitational instability-driven, is that they make the channel maps a little bit wiggly, for lack of a better term. The only feature that you see additionally in the planet-driven model is these little winglets at the local location of the planet. This local redshift and blue shift from that perturbation. And so really when we're looking for spiral-like effects, we're looking for these wiggles in the channel maps. So I want to talk a little bit about warps. I didn't really know what a warp was before starting this project, but it is any misalignment in tilts in the disk. So anytime the disk doesn't lie in a completely flat plane. They can be really subtle, they can propagate through the whole disk, or they can be really extreme where the outer disk separates from the inner disk and it appears at a different angle. In terms of origin, they can be companion-driven. There are other causes that we don't fully understand yet, but they're observed in many places, including planetary rings, debris disks, and even black hole accretion disks. And I have a model of what a black hole accretion disk with a warp looks like here. So you can see that the inner part of the disk is a little bit tilted with respect to the outer part. And here's just a couple more examples. These are a simulation on the left and a sketch of a warp on the right. And so on the left, you see what would be kind of a subtle warp where this bending spiral pattern propagates through the whole disk. And then on the right, you see what could be kind of an extreme warp where these disks physically separate from each other. And so a really great example that we have of a warp in debris disk land is a debris disk called Beta Pictoris. So on the top image, that is data from the Hubble Space Telescope. And you can see this, it's a very edge-on disk. So you're seeing the line of the disk, and then just a little bit, you see this inner part that's tilted. And you can see it a little bit more clearly in the bottom part, which is a simulation. You see that flat plane of the disk, and then this cross pattern from the inner disk. And this warp is really notable because it actually helped in the discovery of an out-of-plane planet in the disk. So there's a planet in Beta Pictoris that's orbiting out of the plane of the disk and pulling this material into this warp pattern. Actually, the rings, the spiral pattern in Saturn's rings is also a great example of a subtle warp because these wave crests don't lie exactly in the plane of the disk. They are elevated and dip slightly. The effect is very subtle, but it's the same general idea. It's also worth mentioning that there's kind of this gray area between warps and spirals. So that beautiful image that we saw of MWC 758 before, we see that there's this spiral pattern in the scattered light, but on the right in that image is actually a warp model trying to simulate the same emission. And it's not perfect, partially due to limitations of the model and partially because protoplanetary disks are a really complex system. You have inflow into the star, inflow from the cloud, planets forming, et cetera. But to an initial extent, you're able to replicate this spiral structure even with a warp model. And then when we simulate Beta Pictoris, we're actually able to see this, we can't see it directly because it's a very edge-on disk, but if we were able to see the face-on view of the disk, through simulations, we think that there's a spiral that's propagating outwards from the eccentric orbit of this planet. So there might come from distinct origins, the spirals and the warps, but they might also not be mutually exclusive. And I mention this because this is the problem that I've been trying to tackle in my project is, as we look at these asymmetries in 49 Ceti, do we think they're indicative of a warp, or do we think they're indicative of a spiral, or maybe something in between, or maybe something completely different? And so to do this, I've been developing models of what these would look like in the disk, and then comparing them to really recent high-resolution data taken from this huge radio array. Yeah.
I'm glad you came. The upper left in your first one, 49 Ceti, and he's got these two bright areas outside the core. What is this wavelength of a particular gas, or what is that attributed to?
That is a really great question, and something that's it's something that I'll talk about a little bit more, and it's actually a really important feature in the disk. We're just looking at the gas. Sorry, this is the dust continuum. So we're looking at the distribution of the dust, and what we're seeing is, from our perspective, it looks like an overdensity in those particular points. it's not a real overdensity, but because the disk is inclined from our perspective, we're just looking at more dust along that line of sight. But there's a really interesting feature with those two pieces of peak emission. So I'm really glad you pointed it out because we'll definitely talk about it in a minute. Sure.
Online, talking about a slide or two ago.
Sure.
They were just asking, some of the explanation of the warp. Is that why some planets with rings have moons that don't align with the plane of the ring?
Oh, that's such a great question. That is a great question. And one that I don't actually know the answer to off the top of my head, but we definitely see it in well, some misalignment in moon orbits are because the object gets captured after the planet is formed. So it's we expect that moons that form with their planet or from a disk would be aligned with rings in a disk, or might form out of the disk. But if they're gravitationally captured later, they might be offset. Definitely, this is the case for Mars's moons. I think it's possible that warps could cause like subtle misalignment in planet moons, but I'll admit that it's not something that I've dug a lot into. So, but that's a really great question, because we definitely see it for debris disks, like in Beta Pictoris. So, yeah. So in terms of the actual research I'm doing, I'm trying to develop models for these two hypotheses and then match them to the data and see if either of them really match. So for our warp model, how we're doing this, we're breaking a simulated disk into individual rings and then letting them tilt with respect to the disk and letting them twist within the disk. And just some like initial pieces of how this model is working. This is a simulation of what a face-on debris disk looks like on the left. And then on the right, I've taken the inner part of the disk, I've twisted it 180 degrees, and then I've inclined it by an extra 20 degrees. So this is just a demonstration of the capabilities of the model. We don't think that warps like this would actually be this extreme, but this is just me testing it to make sure that it works. And I'll be saying it's been giving me a ton of trouble because when you simulate a warp, you break symmetry in the z-axis in a way that becomes really difficult to articulate in code. So I'm still working on that, but so definitely work in progress. But these are some of our initial images. And then I guess I'll also mention that we're pulling these models from other pieces of literature. And spirals and warps have been really well simulated for a 2D plane. But because our disk is at a relatively high inclination, we're looking at it kind of from the edge on, it becomes really important to simulate this in 3 dimensions. And so we can get an idea of how the puffiness of the disk impacts the structure that we're seeing. So that's one of the reasons that we're working on these models, but I'm pulling them from other literature. The basis of the spiral model is, I love this package because they called it Giggle. It's a gravitational instability wiggle, so Giggle altogether. And the effect that it's having on the disk, we're introducing a perturbation to the velocity in a spiral spectra, a spiral pattern. So you can see that it would cause portions of the disk to rotate a little bit faster and some portions of the disk to rotate a little bit slower. And then we're also introducing this surface density perturbation, so parts of the disk that have a slightly higher density than other ones. And just some initial results from this one. This is a spiral and a face-on view, the surface density that I'm simulating as if you were looking face-on at the disk. And then in these images, I'm flipping through those channel maps. So I'm flipping through the changes in velocity of the disk. So we're basically seeing the disk rotate. And we can see the kinematic effect of the spiral model, which I think is really exciting. So in the top, we have a model that's completely symmetric, no spiral introduced. And then in the bottom, we have a model with a spiral. And the effect that you're seeing is, especially at the edges, which you can see in these couple of slides, the channel maps are getting kind of wiggly, which is a little hand-wavy, but what we think is, similar to what we think is happening in real disks. So, and it's also promising because that means if we view a disk that's relatively edge-on, we think that we should be able to see that. So, and in terms of comparing to data, these are our very initial results. And so far, we've only compared to the lower resolution data. So we haven't started to work with the high resolution data yet. But we see some really exciting features. So for both of these models, I've simulated a spiral in the top, a disk with a spiral that's kind of the same inclination and shape that we would see our regular 49 Ceti data in. And I've subtracted off of it all of the material that's rotating symmetrically. The same process has been done for the data that you see in the bottom. So we saw this image a little bit earlier. Again, we're looking at the gas emission, and then we're subtracting a model of, this model of if everything was moving perfectly exactly how we expected it, symmetrically, subtracted that off. And so we're comparing between the model and the data, we're comparing those residuals and seeing what's left over. And what I think is really exciting is that we see some similar features. So we see these bands of emission offset from the major axis of the disk, kind of above and below the plane of the disk. And then we also see these positive and negative features. So we see parts of the disk that are moving faster than we expect, and then we see some parts of the disk that are moving a little bit slower. And so you can see the slides really well now, so I think that's a benefit, but oh, there we go.
Stay the ball here. Can't turn.
Thank you. And so I think this is definitely a first pass, and we want to try different spirals to see if they work differently in the disk and different angles. But very initially, at least we see these similar features, and so we think that the spiral hypothesis could be pretty promising. Haven't quite gotten there with the warp models, but we have gotten to image directly our high resolution data. And so this is our carbon monoxide emission, in addition to the continuum emission that we saw earlier. And I think this is really exciting because this is the highest resolution data in carbon monoxide that we've ever gotten to see for 49 Ceti. And so the features that we see in here are like, I don't know, I kind of feel like I'm the first person that gets to look at them. I think it's interesting. So the feature is really subtle, and I think it will be more pronounced once we subtract that symmetric model from it. But very initially, again, a little hand wavy, but in these bands that are closest to us, to me, they seem kind of wiggly. And given the effects that spirals have on our models, I think that's kind of promising for our spiral or warp hypothesis. And I was actually at a really interesting talk earlier today about looking for the kinematic signatures of planets in particular on disks like this. And so one of the things that I'm going to be looking for in this data is flipping through these channel maps individually, looking at these velocity slices individually, trying to see if we can see that subtle Doppler shift, the slight blue shift and red shift that you see at the direct location of the planet, and see if we can see that effect on the channel maps for this data. My other promising piece for the warp hypothesis, and this is why I'm so glad that you mentioned those peak sites of emission. Really, one of the features that is indicative of a warp in 49 Ceti is that when we look at the disk continuum, these peak emission features are offset from the angle of the disk. And as I've been looking at papers that explore warp simulations, this is a simulation of how a warp might change over time with an inclined, completely inclined disk with an inclined planet in the middle. And I just gasped when I saw this figure because I felt like they took an image of 49 Ceti and put it straight in there, because what you see in that figure is that the peak emission from the dust is offset from the major axis of the disk. I wonder if I can point to it. Yeah, you have this kind of twisting effect. And so even though this is just a simulation and it's not of our disk, I think this is really promising, this hypothesis. And so this is very much still an in-progress project. This is what I'm working on for my master's thesis. And so kind of the next step are going to be finalizing the warp model and seeing if the kinematic signature is similar to that of a spiral or something completely different, if we think those two things will be distinguishable or not. My guess is that it will kind of look like the wiggles that we've seen in the spiral models, but we don't really know until we test it. And then we'll be comparing to higher resolution data. So if I'm just going to jump back a couple of slides. It's a little bit hard to tell if this fits well, if this data fits well with the model or not, because we're limited by the resolution of the image. And so it makes me really excited to dig more into this high resolution data, because I think we'll be able to distinguish in much greater detail whether it matches our models or not. And then we've been focusing on the gas, but the next step will be trying to apply these same models to the dust and the disk also, and to see if those match with the dust continuum data that we have. And I just have a couple more slides. So I promise I'm almost done. But in terms of origins, it's really an open question. We know that for 49 Ceti and debris disks generally, they're probably not induced, these, a spiral or warp feature is probably not induced by a gravitational instability, because even though they host gas, the gas is very diffuse as compared to the protoplanetary stage. So we think it does not have enough mass to propagate a gravitational instability spiral like you would see in a galaxy or in a protoplanetary disk. So I think the next probable cause for a planet, for a spiral or a warp, is a planet or companion within the disk. And actually, recent analysis of the puffiness in 49 Ceti, how thick the disk is, kind of points to multiple dynamical populations, which could be, we see in our own Kuiper Belt, because it could be caused by either the presence of planets or more so the migration of planets through the system. So I think it is definitely a possibility. We also think these features could be caused by a stellar flyby for the system. We also think that stellar flybys are not common for systems that don't have, or aren't in stellar multiplicity, so don't have direct companions. 49 Ceti is in a loose collection of stars called the Argus collection, but it doesn't have any, that we know of, it doesn't have any direct companions. Magnetic fields could also play a factor, but unfortunately magnetic fields are super hard to model. And so there's this running joke in astronomy of like, okay, we don't really know what's causing these things, and we know magnetic fields play an effect, so it's probably magnetic fields, but I'm hoping that it's a planet so we can pin it down a little bit more distinctly. Radial flows are something that you see in protoplanetary disks in particular, as you have gas that's inflowing towards the star or falling in from the cloud, but less so in debris disks. And it could also be a misalignment between the spin of the star, axis of spin of the star and the disk. So we're not sure yet if we distinguish a feature, what it could be pointing to, but my gut is kind of leaning towards a planet or something that we just don't understand yet. And I just want to end with why I think this type of research and why I think 49 Ceti in particular is really interesting in terms of the entire field of astronomy. We're just getting to this point with disks like this, so we can start to infer planet activity from the kinematics and from the structure of the disk. And so I think this is really promising in terms of understanding how planets form within the disk and how this informs planet formation theory, and also in terms of discovering new exoplanets potentially. The gas mass in debris disks is actually not really well constrained. We know that it has to be relatively diffuse, but exactly how much of it is really hard to determine. We think a lot of it is hydrogen, but hydrogen is really hard to observe at radio wavelengths. It doesn't emit in the same way that carbon monoxide emits. So it's really hard to pin down how much is actually there. But if we can find a feature that is tying the dust and the gas together, and we're able to model that in detail, we could start to back out how much gas is in this phase from that. And from there, the origins of the gas as well, whether it's being released at this debris disk stage or it's being inherited from the protoplanetary stage. And I'm really trying to write this code in a way that it can be run for other disks as well. And so in that, I wonder if I can jump back to the beginning. I will in a second anyway. In that big survey of debris disks, we found many with asymmetries and not ones that were similar to 49 Ceti, but ones that are interesting in their own distinct ways. And I'm really hoping that I can build these models in a way that can be run with those disks as well. And we can start to guess on how prevalent these structures are, and maybe viewing them in other systems will give more of an indication to their origin as well. So I'm doing it in Python. Yeah. Yeah. I think Python is like the go-to for astronomers. Although part of the model that I pulled this from, a part of it was written in Fortran, and I was So luckily I didn't have to interface with it that much, but that did give me a good jump scare. Yeah. So that's all I have. This was a really fun talk for me to give and put together. So thank you so much for letting me come, and I'm really happy to answer any.
One thing I'd like to point out before he takes more questions, did you notice that image of M61 was up there?
Yes,
One
yeah.
of the people credited, our very own Rob Getler.
Wow, that's incredible. Hold on, back up.
He's a radiologist by trade, so he sees more things in the structure of these things than was more.
Wow.
Yes.
That's so exciting. I'm so glad that I chose this image.
What he's been doing the last versus taking ESA, Hubble, and other observatory data and then processing it for image share rather than just data presentation.
Amazing. It's a gorgeous image.
It's responsible for a good percentage of the astronomy picture of the day.
Really?
Yeah, and at one point he had more than Hubble did.
That's really impressive. Yeah. I think
It's been written up, including a little story about how he puts a ladder up to the street light outside his house and puts a.
And that was 25 years ago too, Chris. Now he goes to Suaru and takes 30.
I talked to him because it's not actually, he's getting pictures from the web.
Yes.
Not his own pictures.
Yeah. Right, correct. He started, in fact, the last time he even had astronomy equipment, he gave it to me to give the needy club members and I passed it all out. He's got 4 books out now too, if anybody's interested.
Anybody online have any questions for Theo?
We have one right here in the room.
oh yeah.
So the modeling you're doing,
Uh-huh.
looks like you've got 2 regimes. You've got the warp disk
Mhm.
and you've got the spiral.
Yeah.
And it looks like that they'll never meet. But when I look at the images, I can't help but feel like, well, if you have a disk that got warped from some originating event, given enough time, left to its own devices, would it just evolve into a spiral?
That is a really great question. And I think it's one that we don't have a good constraint for. But I think I'm going to jump to, it's a good, yeah. The work that I showed was a little extreme, twisting the disk by 180 degrees. But I think if you could imagine like a warp more subtle and propagating through the whole disk, I think it could look quite spiral-like. And yeah, I think really the distinction between the two is if they're sitting in or out of the plane. And yeah, I think if the warp is subtle enough, if it's not extreme enough to tear the disk into pieces, I think it's quite possible to find a spiral.
Working on the scale. Can you speak up? He's working at a scale of about 1,000 AU for a disk, maybe.
Yeah, probably like the radius of the disk that I'm looking at is about 300 AU. So a little smaller.
So these kinematic effects, how relevant are they at different scales? Can you go up to galactic scale? Can you get down? It looks like you're at least presenting planetary ring scale like Saturn.
Yeah.
So across what range is that your kinematic effects? Would you use like, oh, we learned that this is the way to spot a planet. Could you use that in a galaxy for, I don't know, some different purpose?
Goes back to your gravitational statement, doesn't it?
Yeah, that's a really good question. So I think in terms of the global impact of the spiral, I think you could see it at a huge range of scales. You could see it at the scale of rings around planets all the way to galaxies. Like you could see that velocity perturbation. But I think the more local perturbations, you have to be able to gravitationally influence the material that's directly around you. And I think for galaxies, you'd either need something really, really massive, or you would need, or I think you would not really be able to see the effect of, for example, like individual stars, because they're not massive enough as compared to the rest of the system, and things are a little bit too spread out. So I think on the galaxy scale, you'd be able to see the velocity perturbation of the global spiral, but probably not local
I'm thinking
effects.
more along the lines of like a star region.
Yeah, that's that is a question that I haven't thought about. So that's a really good question. I wonder for something like the mass of like a globular cluster too. Hmm. That's true. They are not star forming. But I think definitely, and I think the reason I thought about them is they're really densely packed. Yeah. And so yeah, that's a great question. I don't know. I think it might be something worth looking into. Yeah. Yeah, PhD project. Yeah. Any other questions I could answer? Yeah.
Given there's a planet there,
Mhm.
would there be a way down the line to determine whether or not it would be gaseous or terrestrial?
Oh, that's a really
Question, please.
Yeah, sure. So the question was, if we could detect a planet in 49 Ceti or a similar system, could you guess at the composition if it's gaseous or terrestrial? That's a really great question. I think you can constrain the mass because you can see the gravitational impact it's having on the local parts of the disk. And in fact, it would be really hard to probe smaller planets and terrestrial planets in particular, because just itty bitty little guys. So I think, and then the other part is you would be able to see where in the disk it was. And at least in the solar system, we see this differentiation between our terrestrial planets in the center and gaseous planets towards the outskirts, which is not universal among exoplanetary systems, but I do think it's pretty rare to see, at least we haven't detected any really terrestrial planets. Well, actually, that's not true. Yeah, so I think from the mass, you could probably say, from the mass and the location in the disk, you could probably say it's massive enough to accrete a gaseous cloud, and the location in the disk might point to there's gas there to accrete. So I think if we did find a planet, it would probably be massive and gaseous. Yeah.
So I've got a related question.
Yeah.
So that's 49 Ceti, which is maybe a early. Have other people like looked at like all of these exoplanets being discovered? Most of them are probably quite old compared to what you're looking at, but is there some overlap between these gas dust disks that you are seeing and planets that have been discovered?
Yeah, I think this is a really great question, because exoplanet methods that we currently use and detection through gas kinematics kind of probe different populations. So like you mentioned, first of all, different ages. Three disks are maybe a little bit younger so that we can see them. But also for detected exoplanets, we either need something that's relatively warm and far away from the star so we can take a picture of it directly, or you need something that will, something that's edge-on that will either pass in front of a star or induce a velocity effect on the star to have it move forwards and backwards from our perspective. And so I think for, just in terms of the edge-onness of the disk, it's really hard to see kinematic structure on completely edge-on disks, unless it's a really obvious warp, like you see in Beta Pictoris. And then also in terms of, yeah, so I think actually Beta Pictoris is a great example of the overlap because there is a directly imaged planet that's causing the warp. But I think it's a relatively unique circumstance. And anyway, so this is a complicated answer to your question. I think there is a small overlap, and I think that overlap is in directly imaging planets that are on the young side, so still have this like residual heat from formation and are relatively far away from the star. I think it is pretty hard to look at debris disks that have detectable exoplanets from the radial velocity or transit method. And I think also for a lot of exoplanetary systems that we know about, a lot of them are around smaller, low mass stars, and we expect that their dust systems are pretty small also. And so I think it would be really difficult to see the disk around them. So we're kind of biased towards larger, bright dust and disk systems as well. So there's a complicated answer, but I hope I answered it.
Small overlap.
Yes, yeah. I think that's one of the reasons it's interesting also, because when you see planets, there are maybe a different population you would see with other detection methods.
Any more? Any more in the loop? Or in the loop? I have one. Without any gravitational or kinematic structures that you're looking at here, have you ever looked at the other protoplanetary disk studies like KH-59d, for example? Just, beat the old alma mater.
I honestly haven't personally. This is the first.
That
Yeah.
Wesleyan project started there at the 24,
Mhm.
the old. Went Hubble, Chandra, Keck, and everything. And then finally, I think before Bill retired, it may have been a tertiary protoplanetary system. Just me, it just started looking at all that data and I go, I wonder if that other stuff, because that wasn't radio data then.
Mm-hmm. That is that's definitely a question that I'm gonna follow up. So, I'll definitely ask around Wesleyan about this, because I think that would be fun to be able to look at that disk with these new tools now, because you're right, we can see them at different wavelengths. We can see. Okay, awesome. Yeah, I will ask. I'll ask Bill and I'll ask Seth, and we'll.
Do you know Bill too?
Yeah. He's not in the department as often, perhaps, as he was, but sometimes he gives talks and. Yeah, some really cool research too. So,
It'll just smile about it.
Definitely. Okay, that is on my to-do list.
Sorry, folks.
So we have a question from online. To Theo, what are your plans after graduation?
Oh, that's a great question.
Another great.
Yes, y'all just full of them. Nothing is worse than an audience member. Yes, yeah, I'm just a couple months away actually. So I've applied to a whole bunch of PhD programs, and I really want to keep doing research if I can. It's like just the most fulfilling thing I've ever gotten to do. So I'm just keeping my fingers crossed as I hear back from admissions. But I'm actually going to visit the University of Southern California next week to
Great sub-millimeter array up there.
yeah, that's definitely true. Yeah, and
What universities are associated with Alma?
oh goodness, that's a great question. Almost if
Come on.
yeah.
Guys, heck fast.
I think because the NRAO, which is the government facility that manages a lot of radio stuff in the US, is kind of housed in Virginia, I think, and the Green Bank Telescope is also in West Virginia. I think a lot of radio stuff typically happens at University of Virginia, Penn
Are you
State.
doing radio or sub-millimeter? Both.
Alma does both. Yes, Alma does both. Yeah, and we're
great big Mauna Kea, it's several thousand feet below the summit.
And I think actually my research advisor took data of 49 Ceti with that array for her PhD thesis. So yeah, but we're mostly looking at sub-millimeter. Yes, got to visit there last year while I was taking a radio astronomy class, and it was just, I'm never going to forget that. It was the most incredible experience. It's a beautiful telescope, and it's a beautiful place in the world. So yeah. Green Bank, the Green Bank Telescope in West Virginia.
They have a star party there every year. You can't even use it. You can't get cell phone service within miles.
Yeah, it's in the radio quiet zone. I was at Lick before moving to Connecticut, actually. I worked there for the 2 years between my undergrad and starting the master's program. So that would have been. I don't think I ever got to visit Santa Cruz, but you're right, they do run the observatory. I was working primarily on site at the observatory, which is just outside of San Jose. I was living in the city at that time. And so that would have been 2022 to 2024. Oh, like at the outskirts of San Jose. So, and then moved up to Oakland after that, but then it was a really long drive to get there. Right? Oh yeah. Oh my God. It's such a beautiful view. I love like it's gorgeous telescope, beautiful view of the planets. It's just got that huge aperture. And then also has a really weird and bizarre history. Like James Lick, who founded the observatory, is buried underneath of it. So you can go down and visit his tomb and just really, anyway, I could talk about it forever. Oh, really? Yeah. Yes. Yeah. I think it is still like that. I think that is, I don't think there's a way to fix that kind of chromatic aberration.
No,
But,
they didn't have.
but
It's like 20-inch Clark, it's color fringes, they're acromats, can't be. They're doubles.
yeah, but I think I'm not taking data on it, so I don't really mind because I think they're beautiful to look at. So
What lens correctors and correction for modern acromats, and they designed the Clark's did never published. This same wavelengths don't apply to the old lens. It just doesn't work.
interesting.
We spent $200 just for that. Didn't it?
We should, if there's maybe one more question, I should let Theo go.
Yeah.
Don't see any other coming in on chat from online. Does anyone else online have a question?
I'll start off.
Thank you so much. And thanks again. This was so fun for me. So
Thank you.
Yeah, great speech. Thank you.